can be construed as a transverse magnetization, and so it goes to reviewers that think that we're talking about this, but really something else. Now, the distinction here is that the all-in, all-out state, ideally, there's no sublattice magnetization. Right? Even though it's in, out, each unit doesn't have a magnetization because all the spins add up to 0, right, in the ideal case. And if this locking energy is much higher than the largest field that we apply, we can basically ignore spin canting within each tetrahedron. So, okay, so this is what I'm getting at. Right? All the spins within a tetrahedron add up to 0. So you don't have the NA or NB, they vanish. Right? So it's not really the same thing when you talk about magnetization. The all-in, all-out state is not a conventional antiferromagnet. Now, from our estimate, since the transition is at 120 Kelvin, right? So this is an ordering transition that involves different tetrahedra, and therefore the local energy that locks the spins into all in or all out must be much larger than this transition temperature. So that's a very high temperature. But even if we took this scale, you see that when you apply a field of 2 to 5 Tesla, you know the spins don't, you just completely ignore your external field. There's no canting of the spins. So that's a crucial point. So in an applied field, the dipolar coupling to H is 0. There's no Zeeman energy. And you can show by symmetry, because of inversion symmetry, there's no quadrupolar coupling as well. Right? So the leading coupling is octopolar, and it involves the rank 3 tensor. So this is what Neverfull brought to my attention, that if you calculate the free energy, the leading term is a cubic, a term involving the field to the 3rd power. And this is an unusual situation, right? Because in most magnets, this is not the leading term. But here, this is supposedly the leading term. But this is very odd now because you've applied group theoretic arguments to what chi ijk is. You find the following strange situation. Okay, so step back a little bit. So for octopolar order, the chi ijk, okay, so from the previous expression for the free energy, you can get that mi is given by this, right? And this implies the following, that if you apply a magnetic field, let's say in the AB plane, because of the nature of chi ijk, you get a magnetization response in the C axis. So this is very odd, right? You apply your field, let's say in a horizontal plane, which we will, and the response is not a magnetization parallel to the field, but it's perpendicular to it. Right? But then this brings up the question, which direction? Is it up or down? Well, we can't tell because it's, both are allowed, right? And but the system will spontaneously pick one direction. So that's where the spontaneous symmetry breaking occurs. You can write the magnetization in this way. So this is the perpendicular magnetization that we are looking for, and it's proportional to the product along the 2 axes A and B. Right? Remember, the field is always in the horizontal plane, but the perpendicular magnetization is along C axis. And if omega, which is the chirality term, if it's positive, then it's along positive C, right? But if it's negative, it'll be the other direction. The point is that it could be either, but the system will spontaneously pick one. And that's kind of an interesting situation because you can't predict what the system will do. And are there training protocols that would select one or the other? So we found this very interesting, and so we carry out an experiment. So in the experiment, we will always confine H to the AB plane and search for a C-axis magnetization that is quadratic in the field strength, not linear, quadratic. That's the other strange aspect of this experiment. So we call this a breaking of the Z2 symmetry. It's either up or down. Oh, I should have shown this first. So this repeats the point I'm making. So if your magnetization is up, then it's, roughly speaking, if you fix HA and HB in that order, it's the right-hand rule, but it could equally be the left-hand rule as well. So we can't predict one or the other. And this covers all the points I've made. So to search for this strange possibility, we use a torque and chemical level. The way it works, you have a gold foil, which is very soft, and you put the crystal, which looks like a cube, onto the cantilever, and apply a field parallel to the cantilever, right? So normally when you apply a field this way, you don't expect the magnetization to be perpendicular, right? It usually wants to have a component parallel to the field. But if it did exist, you see, then M cross H will present a torque, will engender a torque along the x-axis. And so it will flex the cantilever down or up, right? Then we have a capacitor, gold plates between the cantilever and the substrate. These days you can measure capacitance to an astonishing resolution, and even a very tiny deflection translates into a measurable, resolvable magnetization. So the crystalline axis, right, remember A and B were the horizontal plane. Define the horizontal plane, C-axis is along Z. So we rotate the A-axis by 45 degrees to the lab axis. It's just for convenience. That's the way my student set up the experiment. Okay, so that's the setup of the experiment. And the observed torque is a product of the magnetization that we're looking for times the field that we apply. And the cosine phi basically is because the torque axis, the system can only respond to torques that are aligned with the x-axis. So that gives you the cosine phi variation. Okay, and you hopefully will pick up three terms. This MS is a spontaneous magnetization whose origin is not so clear to us. Then there's a paramagnetic term that is linear in H. And then finally, the object of interest goes like H squared, right? So the torque then correspondingly will have a linear H term, this one, and a quadratic H term coming from any residual paramagnetic response. And the interesting one is the cubic term. The material goes through a transition where the resistivity rises by 3 orders of magnitude at 120 Kelvin.
Question.
Yeah.
Where is that paramagnetic coming from?
We don't know. So these are. So I gave you the theory for the ideal situation.
So for the theory, you only expect the quadratic term. That's
Right.
it.
Right. Cubic in the torque. Yeah, so when we parse the data at the end, yeah, you'll see all the. I'm showing you all the dirty laundry, so you will see all the dirty laundry at the end.
How do they compare the order of magnitude of paramagnetic and the quadratic?
Well, we don't know what the origin of the paramagnetic
But
term
how
is.
do they compare?
How do we compare? They're comparable, depending on the field, right? Because one goes linear, quadratic in field, the other one's cubic. So at very high fields, the interesting term will always win. Yeah. So there are all these terms that one has to be careful about. But you see that, you see from the angular dependence that you can actually distinguish them. So at very low temperatures, you see that the torque already shows signs of having these three terms, right? It is actually hysteretic, which is a nuisance, but barring that, you can see that this, I'm sure all of you will recognize, is a cubic curve. Right? It's cubic plus a quadratic. So when you take the when you divide out by h, you find that you get a parabolic term. So remember that when you divide by h, you get what I call the torque magnetization. It's comprised of three terms. The one that is interesting is the parabolic term, right? But then you add to it. Oh, sorry. So what Tian has done here is he has taken the odd part of the curve. So by doing that, the field odd part does not include the quadratic, the paramagnetic term. And actually, that is a fairly large term. But anyway, once you remove that, what remains are these two terms, right? So there is a spontaneous term that lifts the curve up or down, depending on which branch of the hysteretic loop. But the curve that we're focusing on is the field quadratic term. That, we claim, can only arise from a nonlinear magnetization, and it will be interesting to look at how it varies with field directions. But you know, the existence of this term, we claim, already implies spontaneous symmetry here, right? Because, you know, with the alignment of the cantilever and the experiment, when you apply the field in plane, you suddenly see a torque that corresponds to the magnetization up or down, as the case may be. Here, in this case, it's up. So this is already, by necessity, broken the Z2 symmetry. Now you can rotate the field, right? So it's in the plane, and I can rotate it anywhere in the XY plane, and that's the angular position we call phi. And it has this interesting D-wave symmetry. And this is actually implied by the original prediction of Tim and Liang, because, yeah, from here you see that this is the predicted expression, that it depends on the components of h along x and y. And this obviously is a D-wave pattern. Right? So we see a D-wave-like pattern. It's a bit distorted for reasons that I'll come to later. But anyway, it has a D-wave pattern. And the sign of the lobe can be read off from the torque. Right? So choosing a positive sign or a negative sign on the vertical lobe is an expression of the spontaneous broken symmetry. In this case, the way that the data came out, this corresponds to omega equal to 1. All right, so having seen that, so the obvious question then is, can you ever change that? You know, can you ever, because if it's spontaneous, it must happen 50% of the time, right? However, the system, like all magnetic systems, has this hysteretic memory. And so we struggle to try to change it. And it turns out that it's very difficult for reasons that become apparent at the end. So one obvious way to try to change it is, well, cool the system in a field, which we call the field-cooled field, right? That HFC. And we found to our surprise that it does matter. So if you cool the system with the field at 45 degrees to the lattice axis, here along y, right? In this case, the field cooling is in the negative direction. Then you pick up a chirality of +1, it's right-handed. But if you field cool in the opposite direction, it comes out left-handed. And we have no idea why it does that. Right? So this is, as mentioned in this morning's discussion, the memory of the system, but in a very strange way that is unconventional. So this ability to change the sign of the D-wave lobe, depending on the sign of the field cooling, was the first surprise. Okay, before I talk about the other surprises, let me talk about the domain walls. So the system is hysteretic. And we can actually see the hysteresis directly. And it's very large when you get just below the transition temperature. Right? So as a measure of hysteresis, we can take the difference of the magnetization, focusing now on only the perpendicular orthogonal magnetization, and plot it versus temperature. And you see this interesting feature that the hysteresis exponentially dies when you cool down. So many of you obviously remember that the hysteretic loop is caused by domain walls in the ferromagnet, right? They get swept to one side or back to the other. Right? Suppose you cool down the ferromagnet, you initially see domains all over the place, right? But depending on the field direction, the favored domain will expand, and that means that the domain wall gets swept across the center. So hysteresis loops are nothing but the motion of domain walls. But here, this implies that, okay, you get very large hysteresis, but when you cool down below a certain temperature, the motion of domain walls decreases exponentially. In fact, the decrease is exponential and can be fitted to a gap of 170 Kelvin. So here's another way to show it. The red curve is the exponential decay, suppression with the gap 170 Kelvin. So these aren't your conventional block domain wall. And I think this has to do with the fact that what do domains mean, right? So we would think that, well, if this is indeed the all-in, all-out state, one domain is all in, all out. The other domain is the time reverse partner, right? But then there's no block domain wall in between. How the system doesn't couple to a magnetic field at the Zeeman level, so much less so the domain. So what is actually moving the domain wall? So these are all open questions that I think bring up all kinds of interesting paths for theoretical investigation. And surprisingly, we believe these are the first experiments to actually talk about the motion of domain wall, so including Z-Chang's local conductivity measurements. Yeah, so what replaces the usual block wall dynamics? Okay, I mentioned that there was one way to change the sign of the D-wave pattern. Here's another surprise. You can also feel cool with a field that is along the x-axis. Now, initially the system has C4 symmetry. Why does it care whether you feel cool along x or y, right? But it doesn't really, because as I mentioned, there is a distortion of the D-wave pattern. Right? You notice that the y-axis, the lobes are expanded as if it were being stretched compared to the x-axis. So it turns out that it's very sensitive to the field cooling between the two axes. So now I'm field cooling along the x-axis, and now the D-wave lobe is completely rotated by 45 degrees. So that again is a puzzle, but this is so surprising that Tian actually repeated the experiment, I don't know how many times, maybe more than 10 times. Because we just couldn't wrap our head around it. You know, it was like, how can we force the system to respond in another way? So this is very robust. And so this is summarized by here. So cooling along y, you get cosine 2 phi. Cooling along x, you get sine 2 phi. And similarly, when you change the direction, the sign along x-axis, it just flips the sign of the lobes. Okay, the last surprise is that this stretching. Right? So x and y, it looks like it's being stretched along the y-axis. Yeah. So here's an attempt for us to fit this stretching. We find that we can actually more or less recover the curve by adding a term that expresses this C4 to C2 symmetry breaking. And we need a parameter which we call eta. So we're just simply adding a a P wave type pattern to this.